In this lecture, let us discuss about different types of similarity which may help us in scaling wind tunnel models and safety issues in wind tunnel handling. In the previous lecture, we discussed about the very important tool of dimensional analysis and we learnt about the Buckingham pi theorem. So, with that background in mind, let us take the discussion forward and let us try to understand about types of similarity. We remembered having discussed about different relevant variables for an aerodynamics problem, which had to be selected initially to perform the dimensional analysis. And once we performed the dimensional analysis, we ended up having relevant non-dimensional groups and functional relationships between them. So, once you have come up to the point where you have identified the non-dimensional groups, the practical experimenter who has the wind tunnel at his disposal seeks to achieve similarity between the model which is going to be tested and the prototype which has to be designed, which is the actual product on which the wind tunnel test results are going to be applicable. Now, very often you may not be able to match the non-dimensional groups perfectly between the two, that is the reality. With sufficient testing, the model data will reveal the desired dimensionless function connecting the dimensionless groups. For example, if you are experimenting with a circular cylinder, it has a certain span, it has a certain diameter and you have fixed it in a wind tunnel test section and you are experimenting with it. And you want to apply the results on a prototype which has a similar section, but which could be much larger, and in an application where the working fluid could be different, there could be differences in velocities, temperatures, etc. And then you are trying to understand how well your test model results from the wind tunnel can apply on the prototype which will be finally designed. And let us say you have come up with a conclusion that for the circular cylinder experiment, the drag coefficient, which is one of the very important aspects of a circular cylinder, would be a function of Reynolds number, Mach number, some kind of a non-dimensional surface roughness which is indicated by this parameter epsilon by d, where d is the diameter of the cylinder and epsilon is a measure of the surface roughness dimensionally. And then L by d, where L is essentially the span of the circular cylinder. So, you have a model which has a section which is circular and the section has a diameter d and the span of the model is L. So, that is basically the idea. If you zoom deep onto the surface and try to make measurements, you will see undulations on the surface like this, which will give an assessment of the surface roughness, which we are indicating through the epsilon. And you need to note that you may not be able to maintain the scaling in surface roughness between the prototype and the model. Why is it so? Because let us say you are applying the same machining technique to fabricate a very small cylinder for your wind tunnel test here, and the same manufacturing process to build the much larger cylinder which will be part of your prototype. In that case, the epsilons between the model and the prototype are comparable, because you have used the same manufacturing or machining process, but the diameter of the model is often less or much less the diameter of the prototype, and therefore, the scaling epsilon by small d and epsilon by capital D are not going to match. Therefore, you would not always be able to match these non-dimensional coefficients or the similarity parameters which we are talking about. Similarly, the span by the diameter, which gives you a measure of the non-dimensional span, may not exactly match between the model case and the prototype case. Further, the prototype may have different kind of other manifestations, other features on its surface which may not be exactly replicatable on a much smaller scale in the model with perfect accuracy. So, there are therefore lot of mismatch between the model and the prototype. So, this is the real world scenario. Let us try to look at the next point, that flow conditions for testing a model are completely similar to the actual flight conditions of the prototype if all relevant dimensionless parameters have the same corresponding values for the model and prototype. This is the ideal case where we are exactly matching between model and prototype, which means, for example, pi 2, which is one of the pi products for the model with the subscript m, is exactly equal to pi 2 for the prototype. Similarly, pi 3 m is equal to pi 3 p, etc., up to pi k m equal to pi k p. If that happens, then it follows from the above equation that pi 1 m will be exactly equal to pi 1 p, but this is not easy to achieve. We already saw instances of why it is not always possible or easy to achieve it. So, therefore, instead of complete similarity between the model and the prototype, attempt is made to achieve particular types of similarity, and therefore, the significance of discussing the different types, namely geometric, kinematic, dynamic, and in problems where thermal effects are important or thermodynamic effects are important, also thermal similarity have to be ensured while conducting the experiments to the best extent possible. Let us begin with geometric similarity, which is the simplest of all, but one of the most crucial ones. It concerns the length dimension and must be ensured before any sensible model testing is conducted. What is the definition? The definition is, a model and prototype are geometrically similar if and only if all body dimensions in all three coordinates have the same linear scale ratio. It is shown through this diagram. You have the prototype and you have a scaled down model. The scaled down model is an exact scaled down replica. That is what we talk about in the linear scale ratio. All the different body dimensions in the 3 dimensions have been scaled down proportionately to arrive at the model. So, it says that as if you took a photograph of the prototype and reduced it or enlarged it until it fitted the size of the model. So, it is not always that you will be reducing it. Most often we reduce it because our wind tunnels are usually much smaller than our prototypes. Sometimes it could be other way around, if the prototype is small enough and the wind tunnel is large, but that is rare. If the model is to be made 1/10 of the prototype size, for example, then its length, width, height must each be 1/10 as large. Additionally, we have the so called homologous points, which are points that have the same relative location. So, for example, the point which is exactly as at the nose of the prototype maps with the nose of the model. A point on the left wing of the aircraft matches exactly with the corresponding point on the left wing of the model, and so on. So, these are what are called as homologous points. So, the geometric similarity requires that all homologous points be related by the same linear scale ratio. This applies to the fluid geometry as well as the model geometry. So, the fluid domain within which you are performing the test, to that also you have to apply the same scaling. All angles are preserved, all flow directions are preserved, orientations of model and prototype with respect to surroundings must be identical. So, these are the very detailed aspects which try to explain the implications of geometric similarity. Though it is quite intuitive, this is one of the most important similarities which have to be satisfied before any aerodynamic experiments can be conducted. Let us move on to the next category, kinematic similarity. What does it require? It requires that the model and the prototype have the same length scale ratio, which is the geometric part, as well as the same time scale ratio. The consequent implication is that you end up having the same velocity scale ratio between model and prototype. So, the motions of the two systems, the model and the prototype, are kinematically similar if the homologous particles lie at homologous points at homologous times. That is how we interpret kinematic similarity. Therefore, from length scale ratio we have elevated it to a velocity scale ratio by introducing the time scale ratio. Finally, dynamic similarity. What is it? It exists when the model and the prototype have the same length scale ratio, time scale ratio, and additionally force or mass scale ratio. So, this is the augmentation here. Geometric similarity involved length scale ratio, kinematic similarity involved length scale as well as time scale ratio, and now dynamic similarity includes length, time as well as either force or mass scale ratio. If the model and prototype force and pressure coefficients are identical, then dynamic similarity has been fulfilled. Let us see a few more aspects of dynamic similarity to get the concepts more firmly set in our minds. For that, we will divide the flow regimes into incompressible flow and compressible flow, and that too in incompressible flow we will further divide them into flows which have no free surface and flows which have a free surface. What do we mean by a free surface? Let us say you have a river flowing, and when you watch the surface of the river, above it you see the ambient air. The surface of the river deforms. This is an example of a free surface. Flows which do not have any free surface, in which if you have equality between the model and prototype Reynolds numbers, you are going to be able to satisfy dynamic similarity. However, if there is a flow with a free surface, model and prototype Reynolds number as well as Froude number, which is a relevant non-dimensional number for gravity driven flows, have to be equal. I leave it to you to explore what Froude number is all about and how is it connected with gravity driven flows. So, this is a bit of a homework that you should be doing. So, this distinguishes the dynamic similarity requirements for incompressible flow with two kinds of free surfaces, existence of free surfaces. So, in one we do not have deformable free surfaces, while in another we do have. When we go to compressible flows, what all have to be matched? The model and prototype Reynolds number needs to be matched, which is already there in the picture from the incompressible flow point. You need to match Mach number, specific heat ratio, wall to free stream temperature ratio, Prandtl number. So, there are many more which need to be added because of the higher velocities, the compressibility effects and the associated thermodynamic and thermal effects. Let us discuss a little bit more on dynamic similarity. So, we consider two different flow fields over two different bodies, and if they are dynamically similar, a very important aspect would be that the streamline patterns would be geometrically similar. Additionally, distributions of non-dimensional velocity, pressure, temperature, wherever they are applicable throughout the flow field are same when plotted against common non-dimensional coordinates. Additionally, force coefficients are going to be the same. Of course, it is understandable that if you have non-dimensional pressure and shear stress distributions over the two different bodies coming out to be identical, then non-dimensional force coefficients will also be the same. The criteria to ensure that two flows are dynamically similar are the bodies and any other solid boundaries are geometrically similar for both flows, and the similarity parameters which are relevant for the flows are same for the model and the prototype. So, now we have sufficient background to understand dynamic similarity, and we will try to solve a small problem. Let us consider flow over two circular cylinders, one having 4 times the diameter of the other, and the flow over the small cylinder has a free stream density, velocity and temperature given by rho 1, u 1 and T 1 respectively, while the flow over the larger cylinder has a free stream density of rho 2, u 2 and T 2 respectively, where of course, the second cylinder has 4 times larger diameter compared to the first. The density rho 2 is equal to rho 1 by 4, velocity V 2 is equal to 3 by 2 V 1, and the temperature is 9 by T 2 is equal to 9 by 4 T 1. Let us assume that mu and A are proportional to under root T. What do we need to show? We need to show that the two flows are dynamically similar, for which we will consider the Reynolds number and the Mach number to be the relevant non-dimensional parameters. If we write down the Reynolds number for the second cylinder, it is by definition rho 2 V 2 d 2 by mu 2, and then we basically substitute the conditions that rho 2 is equal to rho 1 by 4, V 2 is equal to 3 by 2 V 1 and d 2 is 4 d 1, and mu 2 is 3 by 2 mu 1, because mu 2 by mu 1 are related by a condition like this as defined here. So, that is under root 9 by 4, which is 3 by 2, which is also equal to the ratio of the speeds of sound for the two cases. Thereby, what we end up getting is rho 1 V 1 d 1 by mu 1, which is the definition for R E 1, Therefore, we get a condition RE1 equal to RE2. So, we have maintained equality of one of the important non-dimensional parameters already. When it comes to Mach number, you do a similar process and thereby you get V2 by A2 finally coming up as V1 by A1. Therefore, Mach number equality is also established. So, the two flows can be claimed to be dynamically similar. So, you can understand that in one case the diameter was small, in another case the diameter was larger, and then there were variations in velocity and other flow parameters, but finally the flow field should be looking very similar when scaled appropriately. The features would be very similar to each other, only scaled down or scaled up using the suitable scale ratio. So, the consequence of the dynamic similarity is that the streamline patterns are going to be geometrically similar, which we tried demonstrating here. The non-dimensional pressure, temperature, density, velocity, etc., these distributions are same around the two cylinders. That means, if you plot pressure, for example, as a function of non-dimensional surface distance S by d, the curves would be identical for both the bodies. Similarly, the drag coefficients for the two bodies are going to be identical. That means, CD1 is going to be equal to CD2. They are identical to each other. So, these are the consequences of maintaining dynamic similarity. So, with this we complete our discussion on dynamic similarity, geometric similarity and kinematic similarity, which are the three different kinds of similarity that we learnt about. Now, briefly we will discuss about safety issues in wind tunnel handling, and let us start with low speed tunnels. So, in low speed tunnels there could be failure of testing models or attachments, which can happen for any tunnel for that matter. So, we have to be careful about such accidental situations, and for that the best remedy is to have a safety screen downstream of the test section ahead of the fan, so that that safety screen can arrest failed models or attachments. And then the loads which are acting on the models when you are performing the tests should be well estimated, and accordingly the model attachments should be designed so that they can withstand the loads. It is recommendable that at least two persons who are conversant with the tunnel operation are always present during the experiment. A single person performing the experiment is not recommendable. In large facilities where operators do not have a visible access to the entire facility, there should be provision for alarm bells, which should be rung a number of times before operating the tunnel, and having cameras at different points in the facility can be an additional help. The operator should have easy access to the main switch, which is used to start or stop the tunnel, so that in case of an emergency the operators can cut off the power to the tunnel and stop it immediately. There could also be a panic button close to the tunnel operating room. Additionally, there should be a close watch on the safety of the entire installation, in the sense that there should be routine checks of whether the structure is getting aged and old, especially true for wooden wind tunnels, where aging can lead to some portions of the wooden tunnel yielding to the suction due to subatmospheric pressure inside the rapidly moving flow sections. So, such loose wooden flying objects may hit the fan blades and cause a lot of damage and catastrophe. So, thereby safety screens should be provided ahead of the fan, and in open circuit wind tunnels the operators should avoid moving into the fan area when the tunnel is running. When students are attending laboratory classes, they are also advised to do so, that you should never be moving close to the fan area for open circuit tunnels. So, these are some of the safety issues associated with low speed wind tunnels. Let us have a look at safety issues of high speed wind tunnels. In high speed tunnels, air and other gases are handled at high pressures. So, they are stored as well as handled at high pressures, and therefore, these machineries which are handling the high pressure sections, they have to be tested and certified from time to time, so that we ensure safe operation. Usually, there are several compressors in large facilities, and these have revolving parts, and vibration sensors have to be provided to monitor their vibration levels and ensure that they are within safe limits. Otherwise, they need to be undergoing some maintenance. Safety valves should be provided in the circuit to avoid accidents caused due to accidental over pressurization and consequent catastrophic failure of high pressure tanks and other components. So, safety valves are a must. Oil filters should be provided downstream of the compressor delivery lines, so that we are able to remove oil droplets from getting mixed with compressed air, which could be hazardous. You should also install air dryers to remove moisture which would otherwise condense in the test section. This may not have a catastrophic effect, but it would affect the quality of measurements that you perform in the test section, especially the flow visualizations, because it will make the glass walls of the test section blurred and foggy. The starting loads acting on the model and attachment are much higher due to passage of starting shock. So, appropriate stiffness of the model and attachments need to be ensured, so that they do not yield to the large loads and fail. And there are some common safety issues. That means, you need to have 2 persons who are conversant with tunnel operation to be present during an experiment, like we mentioned for low speed wind tunnel. You need to have alarm bells, you need to have cameras deployed according to the need of the facility, and obviously safety switches etc., which need to be used for immediate shutdown if need arises. So, in this lecture we discussed about the different kinds of similarity, including geometric, kinematic and dynamic similarity, and their role in sizing and scaling of internal models. We ended the lecture by discussing safety issues in wind tunnel handling, both for low and high speed wind tunnels. Thank you.